If you drop a coin inside a bullet train moving at 200 miles per hour, it falls straight down. It does not fly backward. The coin, the air inside the cabin, and your own body are all sharing the exact same momentum. That simple mechanical law, first framed by Galileo, is why you're not being ripped from your chair. Right now you stand on a sphere of rock that spins on its axis at roughly 1,000 miles per hour. That sphere is being relentlessly dragged around a massive fusion reactor at an orbital velocity of 67,000 miles per hour, and that reactor, our Sun, is locked in gravitational freefall, orbiting the galactic center at a speed that defies comprehension. We trust our senses to tell us what is real. Our inner ear senses no acceleration. Our eyes see a fixed horizon. Therefore, the brain constructs a comforting illusion of total stillness. But the reality of astrophysics is far more violent. We are tethered to a mechanical system so enormous that if the gravitational glue holding it together were to suddenly vanish, the sheer kinetic energy of our current trajectory would fling us into the intergalactic void. To understand the cosmos, we first have to admit that our biological senses are constantly lying to us. Watching a spinning system is watching a negotiation between kinetic energy and the forces trying to bind it. Picture a stone tied to a string being swung in a circle. The faster the stone moves, the more tension is required in the string to keep it from breaking away. On a galactic scale, the stone is a star, and the string is the gravitational pull generated by the total mass of the galaxy. If you chart the rotation of the Milky Way, logic dictates that stars at the extreme outer edges should orbit sluggishly, held loosely by the fading gravitational grip of the central core. That is exactly how our local solar system operates. Neptune creeps along far slower than Mercury because the Sun's gravity weakens with distance. But when astronomers measured the actual velocities of stars residing on the galactic rim, they uncovered a mechanical impossibility. Those distant stars are moving far too fast. They are tearing through the void at speeds nearly identical to the stars located much closer to the center. Under the strict laws of orbital mechanics, the centrifugal force generated by this extreme velocity should have flung these outer stars into deep space billions of years ago. To keep a spiral structure of this magnitude from shredding itself apart, a massive inward gravitational pull is mandatory. Yet when we tally the mass of every single shining star, every dense cloud of gas, and every stellar remnant we can detect, the math fails completely. It's the equivalent of an audited ledger showing expenses that far exceed visible capital, yet the account still appears solvent. The visible matter accounts for barely 15% of the required gravitational mass. The remaining 85% is completely missing. It emits no light, absorbs no radiation, and leaves no heat signature. We call it dark matter, but that label is merely a placeholder for a profound physical deficit. The glowing spiral we call our galaxy is really just a thin layer of visible debris embedded inside a colossal sphere of invisible mass. Every shining star we have mapped is a captive trace, locked in a gravitational well made of something we cannot touch. Deep within the geometric heart of this spinning phantom structure lies a point of infinite density. Astronomers refer to it as Sagittarius, a star. It contains the equivalent mass of roughly 4 million of our suns, compressed into a volume no larger than the orbit of Mercury. You might assume that such a massive gravitational anchor is actively pulling the rest of the galaxy into its event horizon. That is a fundamental misunderstanding of how singularities operate in a vacuum. A black hole is not a cosmic vacuum cleaner. It is simply a dense concentration of mass. If you were to replace our Sun with a black hole of the exact same mass, the Earth would not be drawn inward. It would continue along its current orbit indefinitely, merely in total darkness. The stars residing in the dense galactic core circle Sagittarius a star safely, preserved by their own immense angular momentum. However, biological life cannot survive in that central hub. The galactic core is saturated with sterilizing radiation from tightly packed clusters of ancient stars and the occasional volatile outbursts from the accretion disk of the black hole itself. Fortunately, our solar system resides in the quiet outer suburbs of the Milky Way, approximately 26,000 light-years away from the center. Out here, the stellar density drops drastically. Space is far emptier, giving a stable, low-radiation environment where delicate chemical bonds can form over billions of years. In this tranquil region, it takes the Sun 230 million years to complete a single rotation around the galactic core. The last time our planet occupied this specific location in its orbital path, the very first primitive dinosaurs were just beginning to walk the Earth. We enjoy an illusion of permanent stability in this quiet neighborhood. But this peaceful rotation is deeply misleading. Our entire galaxy is currently falling through intergalactic space, completely locked onto a trajectory that ends in a direct intersection with a neighboring giant. For thousands of years, the absolute boundary of human reality was defined by a single glowing band of starlight. Until the autumn of 1924, every respected astronomer on Earth operated under a shared, unquestioned assumption: the Milky Way was the entirety of the universe. The faint cloudy smudges occasionally observed in the night sky were universally classified as local nebulae, assumed to be mere pockets of glowing gas floating safely within our own galactic borders. Then a 35-year-old astronomer named Edwin Hubble pointed the 100-inch Hooker telescope at a specific prominent smudge in the constellation Andromeda. He was not looking to redefine cosmology. He was searching for a very specific type of stellar engine known as a Cepheid variable. Think of a Cepheid variable as the cosmic equivalent of a calibrated lighthouse. These stars physically pulse, expanding and contracting in a highly predictable rhythm. The physics driving them dictates that the slower the pulse, the higher the absolute luminosity of the star. By measuring the exact rhythm of that pulse, an astrophysicist can calculate precisely how bright the star truly is at its source. By comparing that true brightness to how dim the star appears through a telescope lens on Earth, the exact distance can be mathematically derived. It is a flawless optical ledger. Hubble executed the math, and the resulting numbers immediately shattered the established boundaries of human knowledge. The Cepheid star he measured was not a few thousand light-years away. It was sitting at a staggering distance of more than 2 million light-years. The Andromeda smudge was not a local cloud of gas. It was an entirely separate island containing roughly 1 trillion stars, floating across a void of unimaginable emptiness. Overnight, the known universe expanded by an incomprehensible factor. We had finally mapped our closest galactic neighbor. Mapping it, though, revealed a clear and troubling consequence. By analyzing the shifting light spectrum from that massive neighbor, astronomers found Andromeda is closing on us. It is closing the gap, heading straight toward the Milky Way at 250,000 miles per hour. When human intuition processes the phrase galactic collision, it immediately conjures images of kinetic destruction. It makes us picture planetary bodies and blazing suns smashing into one another like glass in a catastrophic highway pileup. But calling it an ordinary crash is a misnomer. Yet when these two colossal structures finally intersect, the event will be completely devoid of physical impact. To grasp this reality, you must quantify the sheer emptiness of a stellar system. Imagine scaling our Sun down to the exact physical size of a single grain of sand. On that proportional scale, the closest neighboring star to our solar system would be another grain of sand sitting more than 4 miles away. Merging one spiral galaxy into another is mechanically identical to blowing a handful of sand through a continent-sized volume of pure vacuum. The mathematical probability of any two individual stars physically striking one another is indistinguishable from zero. Instead of a kinetic crash, we get a prolonged gravitational negotiation between the systems. As the massive dark matter halos of both galaxies begin to overlap, immense tidal forces will exert torque on the visible matter. The highly organized spiral arms of the Milky Way will be stretched, untethered, and eventually shredded. Vast reserves of interstellar hydrogen will violently compress under the shifting gravity, igniting brilliant new clusters of stellar fusion. Over a span of several billion years, the two distinct rotating spirals will bleed together, ultimately settling into a single featureless elliptical cloud of aging stars. We can model this inevitability with absolute certainty because our two galaxies are inexorably tethered to one another. But this localized attraction reveals a profound physical contradiction. If the fabric of the universe has been relentlessly expanding in all directions since the beginning of time, what massive structural framework possesses enough binding energy to override that cosmic expansion and force these two giants to pull together? The gravitational lock between our galaxy and Andromeda is a direct consequence of local density. While the fabric of the cosmos has been stretching relentlessly since the dawn of time, that expansion is not an absolute dictator of motion. It is a baseline pressure, a constant pulling apart of space itself. But in regions where matter is sufficiently concentrated, gravity organizes a localized resistance. The Milky Way and Andromeda belong to a gravitationally bound structure known as the local group. This isolated neighborhood spans a diameter of approximately 10 million light-years. To understand the mechanics of this confinement, you must picture the expansion of the universe not as a physical wind, but as the steady stretching of a vast elastic grid. If you secure heavy iron weights onto that grid using strong tension cables, the surrounding grid will stretch, but the cables will tightly hold the weights together, forcing the local fabric to resist the overarching expansion. Within the local group, dark matter provides those tension cables. The combined mass of roughly 50 galaxies generates a collective binding energy that completely overwhelms the outward pressure of the expanding universe. Space is stretching everywhere outside this local volume, carrying distant cosmic structures away from us at accelerating velocities. Yet inside our 10 million light-year perimeter, the laws of localized orbital mechanics dictate all motion. The local group functions as a closed gravitational ecosystem, but this ecosystem is remarkably unbalanced. While the Milky Way and Andromeda dominate the gravitational ledger, the remaining mass is fragmented into dozens of much smaller, highly vulnerable satellite structures. The structural integrity of these smaller islands is actively being dismantled by the larger host galaxies, revealing a ruthless mechanism of orbital mass transfer that is currently stripping the outer stellar layers from the closest neighbors in our night sky. If you look toward the southern sky on a clear night, you'll see two faint smudges isolated against the dark. These are the Large and Small Magellanic Clouds. They are dwarf galaxies containing roughly 10 billion and 3 billion stars respectively. In the overarching hierarchy of the cosmos, they operate as captive satellites locked in a decaying orbit around the Milky Way, but a satellite orbit is rarely a permanent condition. Because gravitational attraction strictly follows an inverse square law, the pull exerted by the massive dark matter halo of the Milky Way is significantly stronger on the near side of these dwarf galaxies than on their far side. This mathematical differential creates a severe mechanical stress formerly known as a tidal force. Over millions of years, this physical tension stretches the smaller galaxies, systematically overcoming their own internal binding energy. The process acts as a steady gravitational siphon. Stars and vast reservoirs of neutral hydrogen gas are being continuously drawn out, leaving a trailing stellar wake that currently wraps halfway around our galaxy. The Milky Way is steadily siphoning mass from those dwarfs into its own halo, using that raw material to keep its structure and fuel new stars. Within a few billion years, the Magellanic Clouds will lose their structural cohesion entirely and diffuse completely into our galactic halo. The local group is a closed mechanical system, slowly consolidating its total mass into fewer, heavier objects. Yet even as our immediate neighborhood pulls itself tightly inward, this entire 50-galaxy cluster is actively being drawn toward a significantly denser gravitational basin sitting 54 million light-years away. Expand your spatial reference frame by a factor of 5. 54 million light-years away from our isolated neighborhood lies the Virgo cluster. To understand the shift at that scale, you must look at how mass density changes locally. In our local group, a meager 50 galaxies drift across a span of 10 million light-years. In the Virgo cluster, astronomers count up to 2,000 independent galaxies packed into a volume merely 15 million light-years across. You are observing a regional density increase by a factor of nearly 40. The mechanical reality of this environment is fundamentally distinct from the quiet stability of our cosmic suburb. When gravitational proximity reaches this extreme concentration, orbital dynamics shift from slow, predictable cycles to high-velocity intersections. Galaxies within Virgo whip past one another at thousands of kilometers per second. The sheer physical friction generated by massive structures plunging through the dense, superheated plasma that fills the space between them actively strips away their raw, star-forming hydrogen. It is an environment defined by relentless gravitational shear and rapid mass consolidation. Yet according to the laws of orbital mechanics, a densely packed system of 2,000 fast-moving galaxies possesses an enormous amount of kinetic energy. To prevent that energy from scattering the cluster across the expanding void, the underlying physics demands a singular stabilizing anchor. There must be a localized point of mass so dense and so heavy that it can successfully dictate the continuous rotation of an entire cosmic metropolis. Sitting at the exact gravitational center of this chaotic orbital environment is a single elliptical galaxy known as Messier 87. The core of this structure houses a singularity weighing approximately 6.5 billion solar masses. For a sense of scale, compare it to the singularity anchoring our own Milky Way. Sagittarius, a star, contains 4 million solar masses. The central anchor of Messier 87 is more than 1,500 times as massive. This immense mass creates a gravitational well so deep that it dictates the kinetic flow of the entire Virgo cluster. Thousands of independent galaxies are currently locked in various stages of orbital decay around this central point. When a smaller galaxy loses kinetic energy through physical friction with the dense plasma of the intracluster medium, its orbit inevitably tightens. It slowly spirals inward until its internal binding energy is completely overwhelmed by the tidal shear of Messier 87. Nothing is entirely lost. The stellar populations and raw hydrogen of the smaller system are simply stripped and systematically deposited into the mass ledger of the larger elliptical structure. Over billions of years, Messier 87 has grown to span 240,000 light-years. It did so by transferring the momentum and mass of its neighbors into its own structural framework. Yet even as this immense gravitational basin continuously pulls 2,000 galaxies inward, tracing the absolute velocity of the Virgo cluster reveals a striking geometric anomaly. The entire cluster, along with our local group and every galaxy within a radius of 100 million light-years, is sliding through space in the same direction. For decades, astronomers mapped the cosmos exactly like geographers mapping a continent. They recorded the static coordinates of galaxy clusters and plotted them on a three-dimensional grid. But a static map is mathematically blind to the underlying forces governing a physical system. In 2014, a team led by astronomer Brent Tully at the University of Hawaii realized that simply measuring location was fundamentally insufficient. To understand the true architecture of space, they needed to track momentum. They calculated the peculiar velocities of thousands of galaxies, meaning they isolated the specific motion caused by local gravity, and then subtracted the background motion produced by cosmic expansion. They stopped observing where mass was located. They started tracking where mass was flowing. This shift in reference frames changed our cosmic view. By tracing these gravitational currents, Tully and his team uncovered a massive basin of attraction. They discovered that the Virgo cluster was not an independent center of mass. It was merely a minor tributary. Our isolated local group and the densely packed Virgo cluster are both being actively swept along an immensely larger cosmic river. They named this overarching structure Laniakea. But mapping a volume of space defined entirely by its kinetic flow creates a severe mechanical dilemma. If 100,000 galaxies are all simultaneously accelerating along the exact same gravitational riverbed, what invisible structure possesses enough density to reel them all in? To comprehend the physical boundary of Laniakea, you must abandon human intuition entirely. We are no longer measuring isolated distances. We are quantifying an overarching structural volume that spans roughly 400 million light-years. Within this specific gravitational basin, astrophysicists calculate the presence of approximately 100,000 independent galaxies. Scale becomes a weapon against perception at this level. If you mechanically shrink the entire Laniakea supercluster down so that our Milky Way, with its 400 billion stars and its 100,000 light-year diameter, is compressed to the physical volume of a single grain of sand, the resulting supercluster would still sprawl across multiple city blocks. Every other grain of sand within those blocks represents a distinct galaxy. When you map space at this immense resolution, the Milky Way simply ceases to exist as a measurable data point. It is mathematically erased by the sheer density of the surrounding cosmic framework. Yet even as these 100,000 galaxies plunge together through the dark, their collective mass is completely insufficient to explain their overwhelming kinetic trajectory. They are being relentlessly dragged forward by an external gravitational anomaly so massively dense that its true center remains entirely hidden from our optical telescopes. If you stand in a brightly lit room and look out a window into the night, the glare on the glass prevents you from seeing the darkness outside. Our galaxy creates a very similar optical barrier because the Milky Way is a densely packed flat disk of swirling gas and starlight. Looking directly through the galactic plane effectively blinds our optical telescopes. Astrophysicists refer to this obscured region as the zone of avoidance. It is a cosmic blind spot blocking roughly 20% of the external sky. And sitting directly behind that dense curtain of dust is the precise gravitational anchor dictating our overarching trajectory. Astronomers named it the Great Attractor. It is not a single supermassive black hole or a rogue dark star. It is a localized anomaly of extreme mass density, likely a dense convergence of hidden galaxy clusters. This structure exerts a binding force so fierce that it is currently dragging the Milky Way, the Virgo cluster, and the entire Laniakea supercluster toward it at a relentless velocity of 600 kilometers per second. We are caught in a massive gravitational landslide. But when physicists calculate the complete kinetic ledger of this region, an even deeper mechanical reality is exposed. The great attractor itself is not stationary. It is also falling. The gravitational current bypasses it entirely, surging deeper into the cosmic web toward a significantly more massive concentration of matter known as the Shapley supercluster, sitting 650 million light-years away. This colossal structure operates as the ultimate gravitational basin for our entire sector of the universe. Over 8,000 massive galaxies are packed into its core, emitting a gravitational pull that dominates billions of light-years of surrounding space. Every single star, planetary body, and molecular cloud we have mapped so far is currently plunging down this exact gravitational slope. We have been accelerating towards this cosmic basin since the formation of our solar system. Yet the modern mathematics of the cosmos guarantee a brutal mechanical paradox. We are falling through space at blistering speeds, but we will never actually reach the bottom. To grasp this paradox, you must separate the movement of mass through space from the expansion of space itself. We are undeniably accelerating toward the Shapley supercluster at hundreds of miles per second. Gravity is actively pulling us down the geometric slope. But gravity is a force strictly bound by geometry. It weakens exponentially across extreme distances, and the physical gap between our isolated galaxy and the Shapley basin spans roughly 650 million light-years. Across that immense stretch of pure vacuum, a different physical law governs the behavior of space. The fabric of space is stretching. Every cubic unit of the cosmos is expanding. That expansion pushes distant galactic structures away from each other. Our local gravitational current drags us forward, but the expanding volume of space between us and that basin is growing faster than our velocity can close. Consider a runner sprinting on a treadmill. The belt on that machine is moving backward far faster than the runner can push themselves forward at all. We are locked in a high-velocity plunge toward a colossal cosmic basin, yet the actual distance between our galaxy and that basin is relentlessly widening. We will fall forever and we will never arrive. This mechanical defeat of local gravity reveals a profound truth about the overarching architecture of reality. When you zoom out beyond the crumbling borders of our supercluster, you uncover the true skeleton of the cosmos. Galaxies are not scattered randomly across a dark void. They are woven into a pattern so immense it shatters human intuition. This structure is defined not by the light of a trillion suns, but by the mechanics of absolute emptiness. If you scatter a handful of fine sand across a wide black table, human intuition says the grains will settle into a roughly even distribution. We naturally apply this exact same terrestrial logic to the cosmos. For much of modern astronomy, we assume that if you zoomed out far enough, the universe would look like a smooth, uniform fog of isolated galaxies drifting through an empty vacuum. That intuition is mathematically incorrect. The universe is not a random scattering of mass. It is a deeply organized physical architecture. When astrophysicists began mapping the precise three-dimensional coordinates of millions of distant galaxies, a profound structural pattern emerged. Space is not smooth. It behaves mechanically like a colossal cosmic sponge. Instead of floating freely, galaxies are tightly bound to one another, strung together like glowing beads along invisible threads that stretch for hundreds of millions of light years. These threads are massive filaments composed entirely of dark matter. They act as the underlying gravitational scaffolding of reality. Where these invisible filaments intersect, they create zones of extreme physical density These geometric intersections are where massive galaxy clusters, like our neighboring Virgo cluster, are gravitationally forced together. But the most profound geometric feature of this structural map is not found in the glowing filaments, it is found in the spaces between them. By pulling all the ordinary matter into these tight structural threads, gravity has systematically evacuated the rest of the universe. It has carved out immense spherical domains of absolute emptiness, formerly known as cosmic voids. To understand the true mechanics of our physical reality, we must look away from the light and study a region of space so profoundly isolated that if our solar system sat at its center, we would never have known the rest of the universe existed. To understand how a structural matrix spanning billions of light years was constructed, you have to rewind the mechanical clock of the universe back to the first fraction of a single second. The origin of the largest physical structure in existence did not begin on a macroscopic scale. It began at a volume significantly smaller than a single atom. According to the strict mathematical laws of quantum mechanics, a perfect vacuum is physically impossible. On a subatomic level, energy is constantly boiling, creating chaotic, microscopic variations in density. Astrophysicists call these events quantum fluctuations. In a stable environment, these tiny jitters cancel each other out almost instantly. But 13.8 billion years ago, the cosmos was entirely unstable. In a brief epoch known as cosmic inflation, the fabric of space expanded at an exponential pace, stretching far faster than the speed of light. This sudden expansion acted as a flawless mechanical amplifier. It captured those subatomic quantum fluctuations and instantly froze them across a macroscopic grid. Imagine taking a high-resolution digital scan of a slightly imperfect glass marble and suddenly magnifying that geometry until it matches the exact physical size of the Earth. The microscopic atomic ridges on the surface of the marble would become towering mountain ranges, and the tiny indentations would stretch into deep, continental valleys. This is the precise mechanical origin of our cosmos. The microscopic regions of space that started with a fraction of a percent more mass became the gravitational mountains. Over billions of years, those subtle density peaks pulled in dark matter, slowly collapsing into the glowing filaments and massive galaxy clusters we map today. Conversely, the regions that started with a fraction of a percent less mass became the gravitational valleys. Their native matter was systematically drained away by the surrounding peaks, leaving behind expanding domains of pure vacuum. These voids now constitute the vast majority of the physical volume of our universe. And to understand the severe mechanical isolation of existing inside one, we must travel to a specific hole in the cosmic web so impossibly large that its very existence challenged our fundamental understanding of gravity. In the early 1980s, the astronomical community initiated the first large-scale redshift surveys. The primary objective was straightforward. By measuring how much the light from distant galaxies had been stretched by cosmic expansion, researchers could calculate their exact three-dimensional coordinates. The prevailing assumption was that these coordinates would plot a relatively uniform distribution of mass. In 1981, an astronomer named Robert Kirshner and his team aimed their instruments toward a specific patch of the sky within the constellation Boötes. They systematically catalogued the distance of every galaxy they could detect in that sector. But as the three-dimensional map materialized, the data presented a severe physical anomaly. Instead of plotting a dense field of thousands of galaxies, the survey plotted a staggering optical blind spot. They had inadvertently mapped a spherical hole in the architecture of reality spanning 330 million light-years across. To quantify this mechanical deficit, a standard volume of space this immense should contain roughly 2,000 massive galaxies. Kirshner and his team found approximately 60. They had discovered the Beautis void. It is a region of space so profoundly evacuated of ordinary matter that it earned the moniker of the Great Nothing. If you dropped the Milky Way into the geometric center of this colossal vacuum, humanity would not have known other galaxies existed until deep space optical instruments were invented in the 1960s. The physical isolation is absolute, but placing a galaxy inside a structural void sends it along a different evolutionary paths. Galaxies packed into dense filaments face relentless physical violence. A galaxy trapped in the Great Nothing follows a different set of mechanical rules. If you observe a galaxy embedded deep within a glowing filament, you are watching a structure under constant physical assault. The intersection of these dense gravitational threads acts as a severe kinetic bottleneck. Galaxies residing in these crowded regions are subjected to relentless tidal forces. As they plunge through superheated intra-cluster plasma at thousands of miles per second, the sheer physical friction actively strips away their internal reservoirs of neutral hydrogen. This process is a strict mechanical eviction. Without that raw hydrogen gas, a galaxy immediately loses the fuel to form new stars. It ages rapidly. It ultimately settles into a red, inactive, elliptical state. To exist within the dense nodes of the cosmic web is to participate in a turbulent gravitational economy where mass is continuously stolen and stellar fuel is aggressively exhausted. The mechanical ledger operates under a completely inverted set of rules inside the Great Nothing. The 60 galaxies trapped within the Beautis void are not decaying. They are remarkably pristine. Because they are isolated from the gravitational shear of the cosmic web, these void galaxies retain undisturbed reserves of primordial gas. They slowly and efficiently convert this hydrogen into stellar mass, completely insulated from the systemic collisions that restructure their densely packed counterparts. The physical reality of the void proves the exact opposite. Absolute spatial isolation is the only mathematical guarantee of preservation. Yet preserving a pristine galactic structure inside a pure vacuum only matters if the geometry of that vacuum remains static, and as astrophysicists traced the specific gravitational forces required to weave the entire cosmic web together, they discovered that the ordinary matter we can detect accounts for a mere fraction of the structural glue. When you closely examine a glowing cosmic filament, it's natural to assume the visible galaxies generate the gravitational tension that holds the thread together. This is a severe optical illusion. The ordinary matter, the burning stars, the planetary bodies, and the sweeping clouds of hydrogen gas does not dictate the architecture of the cosmos. It is merely a passive passenger. To trace the true mechanical chain of command, we must audit the mass ledger of the universe. The baryonic matter we can optically detect accounts for a mere 15% of the total physical mass. The remaining 85% is dark matter. Because dark matter completely dominates the gravitational ledger, it dictates the shape of the underlying structural geometry. Think of the cosmic web not as a glowing network of light, but as a colossal invisible riverbed carved out by dark matter. When the universe expanded and cooled, dark matter was the first substance to clump together, creating immensely deep gravitational trenches across the void. The ordinary hydrogen gas had absolutely no mechanical choice but to flow into these exact same trenches. The glowing galaxies we map today are not the structure itself. They are simply the water pooling at the bottom of an invisible tectonic fault line. We are tracking the headlights of vehicles moving along a massive highway system at night, mistaking the light for the road itself. The dark matter is the concrete. It weaves the filaments together. It anchors the massive clusters and it outlines the boundaries of the great voids. But if this overarching scaffolding is entirely invisible, completely immune to optical detection, how can physicists be absolutely certain that this specific architecture is not just a mathematical hallucination? The proof resides in the mathematics. To verify that the cosmic web is not merely an optical illusion, astrophysicists constructed a flawless digital twin of reality. In 2014, a massive computational effort called the Illustris project was launched. This was not a visual rendering. It was a strict mechanical simulation. Programmers seeded a supercomputer with the fundamental equations of gravity, fluid dynamics, and the exact estimated ratio of dark matter to ordinary matter. They inputted the initial microscopic fluctuations measured from the dawn of the cosmos, and then they let the physical laws run forward for 13.8 billion years. The machine possessed no predefined map of the modern universe. It only knew the rules of kinetic momentum and gravitational attraction. Over months of relentless processing, the simulation began to structurally organize. Dark matter systematically collapsed into dense, invisible trenches. Primordial hydrogen poured into those exact geometric faults, igniting into digital stars and assembling massive spiral galaxies at the precise intersections. When the temporal clock reached the present era, the computer output a simulated cube of space spanning 350 million light-years. The digital architecture was a flawless structural match to the cosmic web we physically observe. The filaments, the dense clusters, and the vast spherical voids were all mathematically inevitable. We understand exactly how the cosmic scaffolding was built, but a simulated framework only dictates where the mass should logically pool. To physically quantify exactly how many galaxies are actually trapped inside this overarching structure, astronomers had to execute an optical gamble that defied all conventional logic. They had to point humanity's most expensive instrument at absolute darkness and simply leave the shutter open. In the winter of 1995, the astronomical community authorized a severe logistical gamble. Orbital observation time on the Hubble Space Telescope is the most heavily rationed currency in modern astrophysics. Researchers typically bid years in advance to secure a few fractions of an hour to photograph known stellar targets. Yet, the director of the institute utilized his discretionary authority to aim the telescope at a patch of sky in the constellation Ursa Major that contained absolutely nothing. For 10 consecutive days, totaling over 270 hours of orbital exposure, the instrument stared into a profound optical void. To quantify the strict physical scale of this target area, imagine holding a single metal pinhead at the end of your outstretched arm against the night sky. That microscopic geometric footprint constituted the entire boundaries of the observation. Human intuition naturally assumes that staring into an empty vacuum yields a blank image, but optical physics dictates a severely different mechanical reality, because the speed of light is a strict finite constant. A telescope is not merely a spatial magnifying lens, it is a literal time machine. When you look deeper into the physical geometry of space, you are mechanically forced to look backward through the chronology of time. The astronomers were not waiting to see what was currently located in that local void. They were keeping the shutter open to catch ancient photons that had been traveling across the expanding cosmic web since the early epochs of reality. When the exposure finally concluded and the digital data were processed, the image forced us to rethink how dense the universe actually is. That pinprick of supposedly empty space was packed with unseen structure, and it forced humanity to recalculate the estimated mass of the entire universe. When the Hubble Deep Field's digital processing finished, that pinhead-sized patch of sky turned into a staggering density of distinct structures unseen before. It contained over 3,000 distinct galaxies. Every stage of galactic evolution was present: massive spirals, tight ellipticals, and chaotic irregulars were all present. But the true mechanical revelation was not just spatial, it was profoundly chronological. The speed of light ties distance directly to time. So capturing photons from those structures means we see them exactly as they were up to 12 billion years ago. We were not looking at modern galaxies. We were observing the raw, primordial architecture of the cosmos shortly after the initial cooling of the universe. Now extrapolate that finding with strict mathematics. If a random patch of the night sky the size of a pinhead contains 3,000 massive galaxies, then the overarching sphere of the cosmos must be uniformly saturated with them. If you tiled the whole visible sky with that identical pinhead patch, you'd mathematically arrive at more than 100 billion galaxies. Humanity had to instantly discard the notion of a sparse, isolated universe. The cosmic web was crowded beyond our most extreme computational models. Yet, even as this monumental optical ledger was being written, astrophysicists understood that the image was severely incomplete. The 3,000 galaxies captured by the lens were only the structures emitting light at specific visible wavelengths. The physical stretching of space itself was actively hiding a significantly larger population of mass just beyond the technological reach of the telescope. When human intuition processes a photograph of the night sky, we operate under a deeply embedded assumption that optical clarity equates to absolute truth. If an instrument is powerful enough and the exposure is long enough, we believe we are seeing a complete accounting of the physical mass present in that specific direction. The thousands of brilliant spiral and elliptical structures captured in the Hubble Deep Field seem to represent the ultimate mechanical ledger of the cosmos. This assumption is entirely false. The visual data captured by our most celebrated orbital telescope was not a complete record of reality. It was a severely filtered cross-section, dictated entirely by a mechanical limitation in how light interacts with the expanding geometry of the universe. To understand the vast empire of mass that was hiding in plain sight within that image, we must rigorously examine the physical life cycle of a primordial photon. Imagine a single particle of light, a photon, forged in the nuclear furnace of a massive blue star less than 1 billion years after the formation of the universe. When this photon is violently ejected into the vacuum of space, it carries a very specific amount of energy. In the language of wave mechanics, high energy translates to a tightly compressed wavelength. This specific photon enters the cosmic void as ultraviolet radiation, vibrating with intense, rapid geometric peaks and valleys. As it begins its journey toward what will eventually become our solar system, it travels at the absolute speed limit of physical reality, roughly 186,000 miles per second. Over the next 12 billion years, the speed of this photon never decreases. It does not experience friction. It does not slow down. However, the environment it is traveling through is not a static, empty room. The three-dimensional fabric of the cosmos is actively expanding. Every single cubic mile of the universe is stretching, creating new physical volume between the distant stellar origin point and our local galaxy. This creates a profound mechanical consequence for the traveling photon. The light wave is embedded in the fabric of space. As space stretches, the light's wavelength is stretched along with it. Consider a tightly coiled steel spring representing our high-energy ultraviolet photon. If you grip both ends of the spring and pull them apart, the distance between each individual coil physically widens. The spring itself has not disappeared, but its geometric structure has been fundamentally altered. In astrophysics, This exact process is known as cosmological redshift. As our primordial photon traverses billions of light-years of expanding vacuum, its tightly compressed ultraviolet wave is slowly stretched out. As the distance between its peaks widens, it loses its high-energy signature. It drops down the electromagnetic spectrum. It shifts into the visible blue spectrum, then stretches into green, yellow, and eventually deep red. By the time this ancient photon finally crosses the cosmic event horizon and enters our local solar system 12 billion years later, the expansion of the universe has stretched its wavelength so severely that it drops completely off the visible spectrum. It ceases to be visible light, it becomes infrared radiation, it is no longer a color you can see. It has been mathematically reduced to a faint transmission of heat. This mechanical reality presents a massive engineering barrier for orbital observation. The Hubble Space Telescope was an architectural marvel of the 20th century, but it was fundamentally designed to mimic the optical range of the human eye. Its primary mirrors and charge-coupled device sensors were highly optimized to capture ultraviolet and visible light. To physically detect a photon, a digital telescope utilizes a grid of silicon pixels. When a high-energy visible photon strikes the silicon, it possesses enough kinetic impact to knock a single electron loose, creating a measurable electrical charge. But an infrared photon, stretched out by 12 billion years of cosmic expansion, no longer possesses the kinetic energy required to dislodge that electron. It simply strikes the sensor and dissipates as a microscopic fluctuation of thermal energy. Furthermore, the physical chassis of the Hubble Space Telescope operates in a harsh thermal environment. Orbiting the Earth, it is constantly exposed to intense solar radiation and the reflected heat of our own planet. The satellite itself physically warms up. If you attempt to use an instrument operating at room temperature to detect the incredibly faint heat signatures of deeply redshifted galaxies, the sensor is immediately blinded by the thermal glow of its own internal hardware. It is the exact mechanical equivalent of trying to identify a single firefly hovering inside a blazing foundry. Therefore, when Hubble stared into that microscopic patch of the Ursa Major constellation for 10 consecutive days, it was entirely blind to the oldest and most distant galactic structures. The 3,000 galaxies it successfully recorded were only the structures that were either close enough to our local group or intrinsically burning so bright in the extreme ultraviolet that their stretched wavelengths still managed to land within the narrow visible window of the silicon sensors. Occupying the exact same optical coordinates, it sat directly behind, between, and vastly farther away than the visible galaxies in that photograph. It was a hidden ocean of cosmic mass. Trillions of solar masses of ancient stellar fusion were striking the primary mirror of the telescope every single second. They were completely undetected. The expanding universe had effectively cloaked most of the cosmic web in infrared, hiding it from our optical instruments. Astrophysicists fully understood that the deep field images were heavily biased optical fragments. They knew the visible galaxies represented only a fraction of the true gravitational architecture. But this created a severe mathematical dilemma. If the fundamental laws of thermodynamics and optical engineering absolutely forbid your telescope from detecting the oldest mass in the universe, how can you possibly calculate the true number of galaxies hidden in the dark? When an optical instrument's physical limits prevent us from seeing the universe's full architecture, human intuition often tells us to wait for better technology. We assume that scientific progress is strictly a matter of building a larger mirror or deploying a more sensitive thermal sensor, but astrophysics does not always have the luxury of waiting decades for the next generation of orbital hardware. When observational tools hit an absolute thermodynamic wall, researchers do not stop looking. They completely change their methodology. They stop relying on raw optical data. They pivot to the relentless logic of statistical mathematics. If the expanding geometry of the universe physically stretches the light of the most ancient galaxies into an invisible infrared wavelength, you can no longer count those structures by simply looking at a photograph. You have to deduce their existence by tracking the undeniable gravitational footprint they leave behind. You have to audit the mechanical ledger of the cosmos. In 2016, an astrophysicist named Christopher Consolis at the University of Nottingham launched exactly this kind of cosmic audit. He and his team understood the severe optical bias of the Hubble Deep Field images. They knew that the 3,000 glowing spirals and ellipticals captured in that famous pinhead of space were only the brightest and most massive objects in that specific geometric corridor. Consolis set out to mathematically quantify the invisible structures hiding in the dark. To accomplish this, his team did not point another telescope at the sky. Instead, they gathered all the existing observational data from multiple deep space surveys and began dividing the observable universe into chronological slices, because looking deeper into space is mechanically identical to looking backward in time. They mapped out the physical density of the universe across different epochs. They isolated a slice of space as it existed 2 billion years after the Big Bang, then another slice at 4 billion years, continuing all the way to our current local era. They were searching for a specific structural pattern. They needed to understand exactly how cosmic mass reorganizes itself over extreme spans of time. The fundamental framework they utilized is known as the hierarchical model of galaxy formation. In the early universe, galaxies did not spontaneously emerge as the colossal, perfectly organized spirals we see in our local neighborhood today. The primordial cosmos was dominated by vast swarms of dwarf galaxies. These early structures were small, incredibly faint, and packed with raw hydrogen gas. Over billions of years, these dwarf galaxies were relentlessly pulled together by dark matter filaments. They collided, they merged, and they systematically consolidated their mass. A giant elliptical galaxy dominating a modern cosmic cluster is not a single original structure. It is a massive gravitational graveyard. It is the consolidated physical remnant of hundreds, perhaps thousands, of smaller precursor galaxies that smashed together over a span of 10 billion years. This hierarchical merging process operates under strict laws of physical conservation. Mass cannot simply materialize out of a vacuum. If you observe a specific number of highly massive galaxies existing in the modern cosmic era, the strict mechanical ledger of the universe demands that a proportionally larger number of small, low-mass dwarf galaxies absolutely had to exist in the earlier chronological slices to provide the raw building blocks. This is the quantitative metaphor at the heart of Consolis's research. Imagine auditing a massive industrial supply chain. If you stand at the end of an assembly line and count 100 completed machines, you do not need to physically see the original raw materials to know they existed. You can mathematically deduce the exact tonnage of steel, the precise number of bolts, and the length of copper wiring that was required to build them. The finished product proves the existence of the unseen components. Consolis applied this exact industrial logic to the fabric of space. He mapped the total mass of the visible galaxies scattered across the different epochs of the universe. He then applied the strict mathematical rates of galactic merging. He ran the cosmic clock backward. He calculated exactly how many faint, low-mass dwarf galaxies were required in the early universe to supply the visible mass we possess today. He was plotting what astrophysicists call a galactic mass function. When his team calculated the required density of these early precursor galaxies and compared it to the optical data captured by the Hubble Space Telescope, the deficit was staggering. The numbers did not add up. The math proved that for every single massive galaxy Hubble successfully detected in its deep field exposure, there were 9 other galaxies in that exact same corridor of space that were completely invisible. A factor of 10, 90% of the entire structural framework of the universe had dropped completely below the detection threshold of our most advanced optical sensors. They were either too small, too faint, or too deeply redshifted into the infrared spectrum to trigger a single electrical charge on a silicon pixel. But their physical existence was mathematically undeniable. The visible galaxies simply could not exist without them. For decades, the standard academic consensus estimated that the observable universe contained roughly 100 billion galaxies. It was a number printed in textbooks and taught in universities around the world. Consellis took his audited mathematical ratio and applied it to that baseline. He multiplied the entire structural inventory of the cosmos by a factor of 10. The resulting figure shattered our understanding of our place in the void. 2 trillion galaxies, 2 trillion separate islands of stars, gas, and dark matter floating across the expanding cosmic web, each one potentially containing hundreds of billions of individual stellar reactors, each one hosting an uncountable empire of planetary bodies. The sheer scale of this physical inventory reduces the Milky Way to a statistical anomaly so insignificant that our entire history becomes nothing more than a microscopic fluctuation in a boundless ocean of mass. We had finally deduced the true structural ledger of the cosmos. We possessed the number, but understanding this scale forces us to confront a deeply unsettling kinetic paradox. We now know that 2 trillion galaxies physically exist within the boundaries of the observable universe. Yet, because the fabric of space is being relentlessly stretched by an invisible pressure, the vast majority of those 2 trillion structures are currently being carried away from us faster than the speed of light. We have counted an empire of mass just as it begins to permanently disappear. When the human mind tries to grasp numbers in the trillions, our ability to process them simply collapses. We have an evolved sense for small touchable numbers. We can picture 100 trees in a stand or count 1,000 grains of sand in our palm. But when the ledger of reality expands to 2 trillion independent galaxies, our internal metrics of scale are entirely invalidated. To understand the sheer physical density of this inventory, we must move beyond raw numbers. We need a quantitative metaphor that forces our senses to face the real architecture of the surrounding mass. Let us construct this mechanical audit step by step. In our own spiral galaxy, modern observations estimate roughly 400 billion individual stars today. If we accept the statistical audit that the observable universe contains 2 trillion separate galactic structures, then assign a conservative average of several hundred billion stars to each system, the resulting stellar total for the observable cosmos defies basic comprehension. That total number sits safely in the range of 200 billion trillion stars. In the standardized numeric notation of modern physics, that is a 2 followed by 23 zeros. 200 sextillion individual stellar reactors burn through nuclear fuel, generate intense radiation, and carve out localized gravitational wells across the expanding cosmic web. To give this abstract figure a physical shape, let us step away from the stars and measure something tactile. Let us audit every single grain of sand on the surface of the Earth. Geologists and planetary scientists estimate the total number of grains of sand across every beach, desert, coastal dune, and alluvial riverbed on Earth to be roughly 7 quintillion. That's a 7 followed by 18 zeros. Now execute the comparative calculation. Take every single grain of sand from every beach and every desert on Earth, dump them into a colossal cosmic container, and then multiply that total volume by 30,000. That staggering product, 30,000 Earths, packed entirely to the brim with microscopic grains of sand, still falls short of matching the total number of individual stars burning in our observable universe. The universe is not a sparse, lonely expanse punctuated by occasional islands of light. It is an absolute saturation of stellar mass. Every square inch of the night sky, even when it appears pitch black to the naked eye, is serving as an optical window into a dense, overlapping sea of galaxies. Yet this staggering abundance of stars introduces a profound mechanical contradiction. If the universe is overwhelmingly crowded with 2 trillion galaxies, each hosting hundreds of billions of suns, human intuition immediately demands that the night sky should not be dark at all. If you tile an infinite number of glowing suns across every coordinate of the celestial sphere, every line of sight should eventually terminate on the blazing surface of a star. The entire canopy of space should glow with the blinding luminescence of a permanent noon. This mechanical problem has haunted physics for centuries, formerly known as Olber's paradox. The resolution to this paradox lies entirely within the physical properties of the expanding universe that we have been auditing. The night sky is dark precisely because the universe is not static. It is not infinitely old. Space is actively stretching at an accelerating rate. The light emitted by the vast majority of those 2 trillion galaxies is subjected to a relentless cosmological redshift we examined earlier. As those ancient photons travel across billions of light-years of expanding vacuum, their wavelengths are stretched out of the visible spectrum entirely. They drop into the deep infrared, into microwaves, and ultimately dissipate below our optical threshold. Furthermore, because the universe has a finite age of 13.8 billion years, the light from galaxies residing beyond a certain physical distance simply has not had enough time to reach our eyes yet. We are shielded from the blinding illumination of 200 sextillion stars by the finite speed of light and the expanding geometry of space-time itself. The darkness of our night sky is not an indication of emptiness. It is a brilliant optical illusion caused by a universe that is expanding faster than its collective starlight can completely blanket our local perspective. This realization forces us to abandon any remaining notions of human exceptionalism. If 2 trillion galaxies exist, each operating as a complex laboratory of stellar evolution, chemical enrichment, and planetary accretion, then the chemical processes that formed our solar system are entirely mundane. The atoms of carbon, oxygen, and iron flowing through our biological bodies were forged in the stellar cores of ancient generations that existed long before our sun ignited. Those exact same nucleosynthesis pathways are currently executing across 2 trillion independent systems. The chemical ingredients of life are not a localized miracle. They are a standardized, mass-produced product of the cosmic web. Yet recognizing this vast industrial output of mass does not bring us closer to making physical contact with whatever else might be out there. In fact, it achieves the exact opposite. While the physical abundance of galaxies guarantees that habitable worlds must exist in staggering quantities across the cosmos, the ironclad laws of orbital mechanics and cosmic expansion ensure that we remain entirely, permanently isolated. Even if an advanced technological civilization were to evolve within a neighboring galaxy inside our local supercluster, the physical gap between us is so extreme that communication is structurally impossible. A radio signal or a photon broadcast from a planet inside the Andromeda galaxy takes 2.5 million years just to cross the void and strike our instruments. By the time that signal reaches our ears, the civilization that transmitted it may have risen, flourished, and completely extinguished itself across the span of evolutionary history. When we calculate the true parameters of these 2 trillion galaxies, we are forced to realize that the cosmic web is a vast, disconnected archipelago. Every galaxy is an independent island, locked in its own local gravitational orbit, completely surrounded by an expanding ocean of space that grows wider with every passing second. We can count the islands, we can audit their mass, we can map their trajectories as they plunge down the gravitational slopes of the cosmic web. But we can never cross the deep water between them. As the expansion of space accelerates under the hidden pressure of dark energy, those distant islands don't just stay out of reach. They're picking up speed, vanishing over the horizon one by one, and leaving our local neighborhood to drift through an increasingly dark and silent void. When you face a count of 2 trillion independent galaxies, you are not looking at a repeat of the same stellar systems. You're looking at a vast, chaotic laboratory of physical evolution that produces astonishing, often brutal structural diversity. If you could somehow pilot a vessel across the observable universe and visit every single one of those 2 trillion islands, you would never witness the exact same configuration twice. Every galaxy carries its own history. It has an idiosyncratic set of stellar generations, a unique chemical enrichment, and an architecture forged by billions of years of local violence and collapse. Consider the sheer morphological spectrum catalogued by deep space observation. There are classic grand design spirals like the Milky Way and Andromeda, balancing rotation across sweeping star-forming arms. There are massive giant ellipticals like Messier 87, glowing and quiescent, packed with ancient red stars that stopped forming new material long ago. There are chaotic, irregular galaxies that defy classification, formless churning regions of raw stellar creation. There are ultra-diffuse galaxies, spread so thin they are almost optically transparent despite spanning tens of thousands of light-years. There are ring galaxies born from high-speed collisions that blast circular waves of star formation outward like ripples in a pond. The catalogue continues through lenticulars and starburst galaxies that burn through hydrogen at hundreds of times the normal rate. It includes active galactic nuclei, powered by supermassive black holes, spewing jets of relativistic plasma across millions of light-years. Some galaxies are ancient relics, forged soon after the universe cooled. Others are dynamic nurseries, blazing with the intense blue light of newborn suns. Some are dead husks, stripped of gas by the hot plasma of dense clusters. Others drift alone through intergalactic voids, unbothered by a neighbor for millions of light-years. Every single one of these 2 trillion structures is telling a completely distinct physical story. This immense morphological and structural variety carries an immediate, staggering implication for the physical distribution of life. When human beings look out at our quiet suburban corner of the Milky Way, it is natural to succumb to an intuitive geocentrism, a quiet assumption that our biological existence is a rare, consecrated event in an otherwise sterile cosmos. But the sheer mathematical scale of 2 trillion galaxies completely obliterates that comforting hypothesis. Let us audit the biological probability ledger using strictly conservative parameters. If there are 2 trillion independent galaxies in the observable universe, and each of those systems contains an average of several 100 billion stars, we are evaluating a total population of approximately 200 billion trillion individual stellar reactors. Within that unimaginable mass, let us assume that only a minute fraction of those stars possess stable planetary systems. Let us narrow the filter further and demand that only a tiny fraction of those planets happen to sit squarely within the stellar habitable zone. That narrow orbital band where temperatures allow liquid water to remain stable on a rocky surface. Even when you apply these aggressively restrictive filters, the resulting number of potentially habitable worlds is so profoundly massive that it completely defies biological intuition. Mathematical models evaluating these parameters conclude that the total number of potentially habitable planets in the observable universe scales into the hundreds of quadrillions, 100,000 trillion worlds, where chemical reactions, liquid oceans, and organic compounds can stably interact across geological time. The mathematical probability that the Earth stands as the sole isolated crucible of life across 200 billion trillion stellar candidates is so vanishingly small that it effectively approaches absolute zero. It is not physically impossible for us to be alone, it is simply mathematically absurd. Life is almost certainly a routine mechanical consequence of stellar chemistry, repeating itself across the cosmos whenever the correct elemental ingredients are provided a stable thermodynamic platform. Yet, acknowledging the high statistical probability of extraterrestrial life does not mean we will ever bridge the physical gap to greet it. The vast abundance of habitable worlds does not translate into an interactive galactic society, because the overarching geometry of the universe forbids practical communication. The spaces separating these 2 trillion islands are simply too vast for relativistic travel or rapid information exchange. If an intelligent technological civilization were to successfully emerge within a typical neighboring galaxy, the physical distance separating us ensures that any attempted transmission would require millions of years to complete its journey. A radio signal broadcast from a planet within the Andromeda Galaxy takes 2.5 million years just to cross the local void and strike our instruments. By the time that transmission arrives on Earth, the civilization that launched it may have risen, peaked, and completely vanished from the historical ledger. The cosmic web connects galaxies gravitationally through the invisible scaffolding of dark matter, but it utterly fails to connect them practically. The structural voids are too wide. The overarching expansion of space is too fast. The vast majority of these 2 trillion biological laboratories are completely unreachable. We can build massive orbital telescopes to capture their ancient light, but we can never visit them, we can never touch them, and we can never converse with anything that might be looking back. We are left sitting on a single speck of rock, orbiting an average star, locked inside one average galaxy among 2 trillion, staring out across an ocean of isolated islands. Each island is furiously spinning through its own history, entirely unaware of our existence, separated by expanding distances that grow unbridgeable with every passing second. We are surrounded by an abundance of life's potential ingredients, yet fundamentally marooned within our own cosmic horizon. A reality that forces us to question what happens when that expanding horizon eventually begins to close. Accelerating expansion imposes a severe mechanical limitation on the architecture of reality, a limit defined by the cosmic event horizon. Modern astrophysical observation successfully documents 2 trillion distinct galaxies spanning the grand expanse of the cosmic web, yet that panoramic vista is merely a temporary artifact of our chronological position. Dark energy drives an unrelenting acceleration of space itself, pushing distant structures outward at velocities that eventually surpass the speed of light. Light operates under an absolute speed limit. A photon travels through an empty vacuum at roughly 186,000 miles per second, completely unequipped to accelerate beyond that threshold. Yet the metric fabric of space is unconstrained by speed limits because it possesses no mass. Across extreme cosmic distances, the volume of space expanding between our local neighborhood and the most remote galaxies can multiply faster than a beam of light can cross it. This creates a mechanical failure identical to a swimmer caught in an outward rushing current, pushing forward at maximum physical velocity, while the opposing riverbank recedes at a superior rate. Beyond a certain physical threshold, the metric expansion between our galaxy and the outer cosmic web exceeds the speed of light. Photons emitted from those distant domains enter a losing race against a stretching track. They travel toward our local group at the speed of light. The intervening vacuum expands so quickly it pushes those ancient signals away, permanently locking them out of our future. This boundary establishes the cosmic event horizon, a spherical shell centered on our exact location that dictates absolute causal contact. Structures residing within this radius can still transmit historical light because their photons were launched when the universe was younger and expansion rates were lower, allowing those ancient beams to successfully bridge the gap over billions of years. Conversely, any photon emitted today by a galaxy positioned beyond that precise threshold is severed from our local experience forever. Dark energy maintains a constant repulsive energy density across the universe, while ordinary matter thins out as galaxies drift apart. The stretching pressure of the vacuum never dilutes. Consequently, the acceleration of space permanently wins the long-term mechanical war against gravity. The event horizon steadily reduces its effective causal reach, pulling the boundaries of our accessible universe inward with each epoch. We occupy a rare, privileged window of observational time. A universe 13.8 billion years old allows ancient photons from a vast swath of space to finally cross our cosmic finish line. We map filaments, count trillions of galaxies, and piece together the grand framework of reality because our specific temporal position permits it. But this panoramic view represents a transient luxury. Billions of future years will witness a slow, relentless disappearance. Distant superclusters will cross the threshold one by one. Neighboring filaments will slip over the horizon, their final beams of light striking our descendants' instruments before plunging into permanent silence. Eventually, massive structural nodes like the Virgo cluster will drift past the causal boundary, disconnecting their light from our local neighborhood entirely. Intelligent observers looking up from a planet trillions of years in the future will experience a starkly different night sky. Andromeda will have long since merged with our local stellar system. Beyond that merged core, absolute darkness will prevail. The cosmic web will be gone. Distant clusters will be erased. Pointing a telescope into space will reveal an unyielding black void. Those future astronomers will construct a profoundly flawed cosmology. Isolated within a stagnant, dying island of stars, surrounded by an infinite expanse of emptiness, they will calculate that the universe consists of nothing more than their own home. They will lack any physical evidence, optical trace, or mathematical clue pointing to the 2 trillion magnificent galaxies that populated the vibrant universe we audit today. Recording this inventory amounts to documenting a dying view. The expansion of space actively dismantles the cosmic architecture, isolating every single island of matter into solitary confinement. Confronting this erasure forces a final question about the ultimate fate of the laws that govern existence. Thermodynamic law governs the ultimate destiny of physical reality with absolute authority. Entropy is the master ledger of the cosmos. Over unimaginably long timescales, usable energy continually degrades into waste heat. Every stellar furnace that consumes hydrogen and every galaxy-riding dark matter threads feed the same process. On a microscopic level, particles interacting across space take part in a steady statistical drift toward equilibrium. This is not a temporary setback or a localized phenomenon. It is an overarching architectural law from which no structure in existence can appeal. Long after the cosmic event horizon has severed every external connection, banishing the 2 trillion neighboring galaxies beyond permanent causal reach, our local stellar remnant faces its own internal exhaustion. Stars represent a precarious, highly ordered defiance of entropy, consuming vast reservoirs of nuclear fuel to maintain the outward pressure required to resist gravitational collapse. Across spans of time stretching across trillions of years, the last stellar generation burns through its hydrogen reserves. The sky dims permanently. The final red dwarf stars flicker out, leaving behind cold, dead stellar corpses drifting in absolute darkness. Stellar extinction marks only an intermediate phase in this thermodynamic descent. Following the fading of normal stars, the universe enters a degenerate epoch. In this cold era, the night sky is illuminated only by the faint, ghostly glow of cooling white dwarfs and dead remnants slowly radiating their residual heat into the void. Planets detached from their dying primaries drift through silent orbits, while massive objects gradually exchange orbital energy, causing dead systems to either be dynamically ejected into intergalactic space or swallowed by central black holes. As time marches forward across even more unfathomable epochs, the very structure of ordinary matter begins to unravel. Protons, long celebrated as the permanent, immutable building blocks of chemistry, are subjected to the slow, relentless probabilities of subatomic instability. According to advanced particle physics, these foundational units of matter eventually decay, dissolving atoms into a sparse drift of positrons and electrons. Every planet, every asteroid, and every solid surface disintegrates into a thin diffusing mist, erasing the physical medium of chemistry entirely. Even the colossal supermassive black holes that once anchored the centers of great galaxies are ultimately dismantled by the laws of physics through quantum mechanical interactions occurring at their boundary thresholds. These immense gravitational singularities continuously shed their mass via Hawking radiation over timescales so vast that ordinary numbers lose all intuitive meaning. Every black hole evaporates. They shrink, stutter, and vanish in a final burst of thermal radiation, leaving the universe completely devoid of concentrated gravitational mass. What persists across the metric of space is an unfathomable, perfectly uniform ocean of diluted particles, isolated photons, and expanding vacuum. Temperature differentials, the fundamental mechanical prerequisite for driving any dynamic process, executing any physical work, or sustaining any form of complexity, cease to exist. Every spatial coordinate settles into an identical baseline temperature, achieving a state of absolute maximum entropy across the entire volume of reality. This condition represents the thermal death of the universe. The cosmos arrives at complete thermodynamic equilibrium not through a cataclysmic explosion or a sudden fiery collapse, but through a slow, profound exhaustion of potential. The magnificent architecture forged by quantum fluctuations at the dawn of time, woven together by dark matter filaments and illuminated by trillions of galaxies, dissolves entirely into an unchanging, motionless background. Mechanical motion stops because no energy gradient remains to compel a shift. Information ceases to propagate because every region of space shares an identical thermodynamic reality. Confronting this ultimate destination exposes the profound paradox of existence. Every structure that ever appeared, every burning star, every living organism, every massive supercluster, every intelligent civilization was a temporary local turbulence. They were ripples in a vast ocean of entropy. We are transient ripples born from a physical system, redistributing an initial concentration of primordial energy. The darkness that eventually blankets the cosmos is not an enemy or a destroyer. It is the natural, restful equilibrium of a system that has finally balanced its grand ledger. Cosmic architecture is more than simple filaments. It unfolds as monumental planar sheets that dwarf our entire local supercluster. While early maps of the cosmic web showed glowing filaments meeting at dense nodes, deeper three-dimensional surveys revealed even larger planar structures. Millions of galaxies are arranged into colossal two-dimensional walls, vast sheets of matter that stretch across hundreds of millions of light-years. These megastructures represent the largest coherent spatial arrangements known to physics, forming massive architectural boundaries across the expanding universe. Consider the sheer physical scale of these galactic walls. Structures such as the Sloan Great Wall span distances exceeding 1 billion light-years from end to end. To picture that enormous scale, imagine shrinking the entire Milky Way down to the physical size of a single millimeter. On that same compressed scale, a giant galactic wall would stretch across thousands of kilometers, forming an unbroken continental divide of mass that separates colossal cosmic voids. Within these immense sheets, thousands of galaxy clusters, stellar nurseries, and dark matter concentrations are fused into a single, interconnected framework. They operate under the relentless pull of local gravity. The physical mechanism driving the formation of these walls originates from the asymmetric collapse of dark matter during the early epochs of the universe. When primordial density perturbations evolved under gravity, matter did not collapse uniformly into point-like singularities or isolated linear threads. Instead, variations in the initial gravitational field caused matter to preferentially flatten along specific geometric axes. This is a foundational process in gravitational dynamics, with matter sheets forming first and acting like colossal tectonic plates across the cosmos. Ordinary baryonic matter subsequently flowed along these invisible planes, pouring into the dense nodes where massive clusters eventually ignited. This planar organization shatters the traditional intuition that matter is distributed haphazardly across the void. The universe possesses an underlying architectural geometry reminiscent of cellular foam, where thin, dense walls enclose massive spherical vacuums. Yet the existence of these hypermassive structures introduces a profound theoretical tension within modern cosmology, a direct challenge to one of the most foundational assumptions of modern physics. Standard cosmological models rely heavily on the cosmological principle. This principle posits that on a sufficiently large scale, the universe is fundamentally homogeneous and isotropic, meaning that if you zoom out far enough, space should look essentially identical in every direction, featuring a smooth, uniform distribution of matter without preferred orientations or monstrous anomalies. For decades, this assumption allowed theorists to model the evolution of the universe using simplified mathematical equations that treated the cosmos as a uniform fluid. Giant galactic walls and massive supercluster alignments directly test the boundaries of that assumption. When a single coherent structure spans a billion light-years, representing a significant fraction of the entire observable universe's diameter, it ceases to be a localized fluctuation. It represents a macroscopic anomaly that refuses to smooth out, even at scales where uniformity is theoretically mandated by our prevailing equations. Astrophysicists analyzing these titanic structures face a rigorous interpretive challenge. Either our current understanding of how dark matter clumps across ultra-large scales is incomplete, or the primordial density fluctuations generated during cosmic inflation possessed a much longer wavelength than existing models predict. The universe communicates its earliest history through the sheer physical layout of these walls, signaling that the primordial seed perturbations were far more complex and far-reaching than previously calculated. Mapping these boundaries requires pushing observational technology to its absolute limits. Astronomers must utilize massive redshift surveys, such as the Sloan Digital Sky Survey, to measure the precise spectral displacement of millions of faint, distant galaxies. By calculating their exact spatial coordinates across vast expanses of time and space, researchers can map the contours of these invisible sheets. Each newly discovered wall adds another layer of complexity to our ledger of reality. It shows that the cosmos is not a quiet, orderly expansion, but a dynamic, highly structured tapestry woven by gravity across unfathomable scales. Yet as stunning as these billion light-year walls appear, they are merely stepping stones toward even more extreme structural anomalies. Beyond the largest mapped walls lie titanic alignments of gamma-ray bursts and quasars, structures so vast they stretch our mathematical frameworks to the breaking point, hinting at an overarching organization of the universe that we are only beginning to comprehend. Observing active galactic nuclei pushes optical and spectroscopic instruments to their absolute limits. Quasars represent the most luminous continuous energy sources in the universe, powered by supermassive black holes consuming surrounding gas and dust at prodigious rates. Gravitational potential energy converts into intense electromagnetic radiation as matter spirals inward, causing a single active nucleus to outshine every star in its host galaxy combined. Astrophysicists track these brilliant beacons across the cosmos, utilizing their extreme brightness as lighthouses to illuminate the deep, structural geometry of the expanding universe. Individual quasars trace the underlying dark matter scaffolding, yet their spatial distribution occasionally reveals configurations that defy conventional statistical expectation. Groupings of dozens of these massive energy sources form coherent structures stretching across unprecedented spans of space. Researchers cataloging these extraordinary formations classify them as large quasar groups, entities that represent the most massive known associations of matter in the cosmos. Discovery of the huge large quasar group exposed a megastructure spanning 4 billion light-years from end to end. Evaluating the physical magnitude of this scale requires a rigorous quantitative metaphor. If the entire distance separating the Earth from the Sun is compressed to the thickness of a single human hair, a structure spanning 4 billion light-years would stretch across the continental United States and deep into the oceanic trench network. Scaling down the Milky Way to the physical size of a microscopic grain of sand leaves the huge large quasar group stretching across multiple city blocks of empty space. Standard cosmological frameworks rely heavily on the cosmological principle to maintain mathematical tractability. This foundational assumption dictates that on a sufficiently massive scale, the universe must be homogeneous and isotropic. In other words, mass should smooth into a single statistical average. Theoretical calculations establish a definitive structural threshold for this smoothing effect, placing the homogeneity limit at approximately 1 billion to 1,200 million light-years. Any structure exceeding that scale theoretically violates the foundational premise of a uniform cosmos. Confronting an architectural entity measuring 4 billion light-years directly shatters that theoretical threshold. Discovering a coherent clustering of massive quasars that triples the maximum allowable homogeneity limit introduces a profound crisis into modern astrophysics. Theorists are forced to choose between two equally unsettling conclusions. Either our statistical methods for identifying physical associations are fundamentally flawed, or our standard model of the universe fails to account for ultra-large-scale coherence. Ruling out optical illusions requires rigorous statistical verification. Skeptics argued apparent alignments of distant quasars might be random line-of-sight coincidences. It was the celestial equivalent of seeing shapes in clouds. To test this hypothesis, research teams deploy complex nearest neighbor algorithms and smoothing analyses to evaluate the true spatial distribution of the component objects. Statistical testing confirms that formations like the Huge Large Quasar Group are genuinely physically associated, showing that gravity operated across scales current mathematical models call impossible. Explaining the origin of such colossal formations requires looking backward to the earliest moments of the universe. Primordial density perturbations established during cosmic inflation acted as the foundational seeds for all subsequent structure formation. If quantum fluctuations were stretched across inflationary epochs to generate 4 billion light-year structures, the initial wavelength spectrum of the universe possessed a much greater magnitude than prevailing theories anticipate. The early cosmos was subjected to physical dynamics capable of organizing mass across distances that defy standard thermodynamic calculations, challenging the cosmological principle. Forces theoretical physics to expand its conceptual boundaries. The universe consistently demonstrates an architecture far more intricate, massive, and interconnected than our simplified equations predict. Every deep sky survey uncovers new anomalies that push our analytical frameworks toward their breaking points, reminding researchers that our ledger of reality remains incomplete. Decoding these ultra-large structures requires continuous refinement of spectroscopic mapping techniques. Astronomers process millions of individual spectra, calculating precise redshifts to map the distant universe in 3 dimensions. Each verified megastructure adds another complex data point to our understanding of cosmic evolution, linking microscopic quantum fluctuations to macroscopic structures. Physical reality stubbornly refuses to conform to human preference for simplicity and uniformity. The existence of large quasar groups shows the cosmos organizes itself on scales that dwarf our current models. It invites future physicists to probe the expanding void and rethink the basic rules that govern space's architecture. Mapping the 3-dimensional topology of the universe required abandoning the flat, 2-dimensional projections that had constrained astronomical research for centuries. Traditional star charts treated the night sky like the inner surface of a celestial sphere, flattening profound spatial distances into a single visual plane. Overcoming this optical illusion demanded a completely new observational approach, one that substituted static spatial coordinates with precise spectroscopic measurements of galactic velocity and recession. During the late 1980s, astronomers Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics embarked on a systematic redshift survey designed to cut deep slices through the local universe. By capturing the optical spectra of thousands of galaxies and measuring the precise degree to which their spectral lines were shifted toward the red end of the electromagnetic spectrum, they could calculate each galaxy's exact line-of-sight distance based on the expanding metric of space. That matrix of spatial coordinates let them produce the first true 3-dimensional maps of cosmic architecture. They constructed the first true 3-dimensional maps of cosmic architecture, moving beyond surface appearance into actual spatial depth. The resulting data visualization shattered conventional expectations of how matter should be distributed across space. Instead of a uniform fog or a random scattering of isolated clusters, the mapped galaxies organized themselves into a sharp, contiguous geometric boundary. They had discovered what the scientific community immediately recognized as the CFA Great Wall. It was a colossal sheet of galaxies stretching across 500 million light-years, standing 20 million light-years thick while spanning a relatively narrow vertical plane. Visualizing this structure requires a precise quantitative metaphor. Imagine a colossal metal sheet stretched across half the distance from our local neighborhood to the visible horizon, with millions of glowing stellar cities densely embedded across its surface. The CFA Great Wall operates as a massive tectonic plate of ordinary and dark matter, dividing the surrounding cosmic landscape and forming one side of a vast enclosed void. Discovering this planar sheet proved that the architecture of the cosmos possessed an inherent order far more complex than simple spherical clusters or isolated filaments. Gravity had not simply pulled matter into localized clumps, it had orchestrated a coordinated, large-scale collapse along preferred geometric axes. Matter had flattened into sheets, creating sprawling cosmic boundaries that separated immense volumes of absolute emptiness. Subsequent mapping efforts confirmed that the CFA Great Wall was not an isolated anomaly. As deeper surveys swept across wider sectors of the sky, astronomers uncovered an intricate network of intersecting walls, sheets, and filaments, all framing the massive spherical voids that dominate the volume of the universe. These structures demonstrated that the cosmic web is fundamentally cellular, resembling the complex foam structure of boiling liquid rather than a random distribution of points. Analyzing the physical formation of these immense walls requires tracing the evolution of primordial density perturbations established during the earliest moments of the universe. When the cosmos underwent rapid cosmic inflation, microscopic quantum fluctuations were stretched across macroscopic scales, creating subtle variations in mass density. Regions that started with slightly higher density possessed stronger gravitational attraction, drawing in surrounding dark matter and ordinary gas over billions of years. However, gravitational collapse in a dynamic universe does not occur symmetrically in all directions. Mathematical modeling demonstrates that gravitational instability naturally forces matter to collapse first along a single axis, forming flattened sheets or pancakes. Next, matter collapses along a second axis, turning those sheets into intersecting filaments. Finally, matter consolidates along the third axis, creating dense cluster nodes at the intersections. The Great Walls mapped by modern astronomy represent the physical manifestation of that initial axis-dependent gravitational collapse. They are the main sheet-like components of the cosmic web, the first large structures to freeze out of the expanding primordial plasma as the universe cooled and as mass sorted into its large-scale distribution. Within these sprawling sheets, galaxies aren't fixed in place. They're in a constant gravitational exchange. Smaller dwarf galaxies stream along the planar highways and feed larger host systems. Dark matter halos merge, forming the massive gravitational wells that help fuel ongoing star formation. This internal dynamism means the walls are not inert monuments. They are active, evolving ecosystems of mass transfer. Understanding their internal mechanics provides the critical bridge between the sweeping macro structure of the cosmos and the localized stellar dynamics we observe in our own backyard. Mapping these distant boundaries pushes observational technology to its absolute limit. Because light takes hundreds of millions of years to cross these megastructures, astronomers are not just mapping spatial topography, they are looking back through evolutionary history, watching how vast sheets of galaxies assembled over intermediate epochs Every newly charted wall adds vital data to our understanding of cosmic evolution, bridging the gap between microscopic quantum seeds and macroscopic architectural marvels. Yet as majestic as these 500 million light-year walls appear, they point toward an even deeper realization about the geometry of existence. The walls themselves are framing devices built around vast abyssal regions so empty of matter that they force us to rethink our basic definitions of reality. Enormous spherical expanses spanning hundreds of millions of light years are frequently mischaracterized as passive vacuums, static regions where matter simply failed to materialize during the early formation of the cosmos. Physical reality is vastly more dynamic. A cosmic void functions like an active evacuation engine driven by steep gravitational pressure gradients that steadily drain its matter over vast stretches of cosmic time. Surrounding walls and massive intersecting filaments exert an overwhelming collective gravitational pull, functioning like enormous cosmic siphons. During earlier epochs, when the universe possessed a higher average density, subtle underdensities existed as minor quantum fluctuations. As surrounding regions collapsed into dense nodes under the command of dark matter, their immense gravitational wells drew in every accessible parcel of ordinary and dark matter. The void did not empty itself, it was aggressively emptied by its neighbors. Picture a vast network of kitchen sponges submerged in a draining basin to visualize this mechanical process. As the sponge's matrix contracts and pulls water toward denser channels, the intervening pockets of fluid are squeezed out, leaving nearly dry cavities. The cosmic web functions identically. The dense filaments and massive walls act as converging sponges, drawing in the fluid of space and leaving behind expansive regions where matter density drops to a tiny fraction of the cosmic average. Galaxies trapped within these colossal vacuums do not remain stationary. They experience a complex internal hydrodynamics governed by peculiar velocities, individual mechanical motions decoupled from the general expansion of the universe. Because the surrounding perimeter walls possess massive gravitational fields, galaxies inside a void are constantly subjected to a net outward pull. They slide down a gravitational slope from the inside out, accelerating away from the empty center toward the dense boundary walls. This peculiar velocity profile creates a unique mechanical environment. Unlike galaxies crowded into dense clusters where high-speed collisions and tidal stripping tear gas reserves apart, void galaxies drift in relative tranquility. Yet their spatial trajectory is relentlessly outward. They are pulled toward the perimeter, while the empty space beneath them stretches at an accelerated rate. Expansion mechanics inside a void differ fundamentally from the rest of the universe. Dark energy, the constant repulsive pressure of the vacuum, encounters virtually no resistance from local matter density inside a void, rendering its influence entirely unhindered. Standard matter exerts local gravity that attempts to slow down expansion, but inside an abyssal void containing almost zero matter, gravity offers no localized braking power. Consequently, the local metric of a cosmic void expands at a noticeably faster rate than the dense filaments surrounding it. Voids stretch out faster than the rest of the universe, functioning as expanding bubbles within the cellular foam of reality. Light traversing these colossal vacuums carries a subtle signature of their internal dynamics. Entering a void forces a photon to fall down a shallow gravitational potential well, gaining energy. Exiting the void on the opposite side requires climbing back out of that well. However, because the void itself actively expands while the photon crosses it, the gravitational well flattens beneath the light wave. The photon retains a net surplus of energy, altering its temperature and creating an observable imprint on the cosmic microwave background radiation known as the integrated Sachs-Wolf effect. Studying the internal pressure gradients and expansion rates of cosmic voids provides astrophysicists with an independent laboratory for testing the nature of dark energy. Dense clusters test gravity in regimes of extreme mass, whereas voids test the fundamental behavior of empty space under zero-resistance conditions. They represent active thermodynamic systems governed by the interplay between retreating mass and expanding spacetime rather than simple absences of matter. Observing these regions requires sophisticated statistical analysis of spectroscopic redshift surveys. Astronomers calculate three-dimensional density fields to map the exact boundaries, volume profiles, and internal velocity dispersion of each void. These measurements reveal that voids are not perfectly spherical. They are deformed, elongated, and interconnected through complex tunnels and channels that allow minor filaments to bridge across the emptiness. Comprehending the internal mechanics of these hypermassive vacuums shifts our perspective on the entire cosmic web. Architecture across the universe is defined as much by what is missing as by what is present. Every void stands as a monument to gravitational migration, marking the spaces where matter once resided before being swept away by the relentless tides of cosmic evolution. Standard cosmological models operate on a foundational assumption of statistical randomness regarding peculiar velocities. Once researchers subtract the overarching expansion of space, the individual motions of galaxy clusters across the cosmic web should exhibit a randomized isotropic distribution, drifting in disparate directions with no preferred cosmic vector. Yet, empirical data gathered from deep space surveys and microwave background measurements exposed an extraordinary kinematic anomaly that directly challenges this foundational premise. Massive galaxy clusters distributed across millions of light-years do not drift randomly. Instead, they exhibit a coordinated bulk motion. Entire clusters are streaming at blistering speeds toward a specific uncharted sector of the sky between the constellations Centaurus and Vela. Astrophysicists designated this mysterious large-scale motion as dark flow. To visualize the mechanical impossibility of this phenomenon, imagine observing an immense flotilla of ocean liners scattered across different hemispheres of the globe. Yet every single vessel is independently steering its course into the exact same invisible underwater jet stream with absolute precision. Detecting such a subtle kinematic shift required innovative observational techniques capable of probing beyond standard optical astronomy. Researchers turned to the cosmic microwave background, the thermal remnant radiation left over from the early universe. As ancient microwave photons traverse intervening galaxy clusters, they interact with hot, energetic electrons populating the intracluster gas via inverse Compton scattering. This phenomenon, known as the kinematic Sunyaev-Zeldovich effect, imparts a minor temperature distortion onto the background radiation depending on the cluster's actual line of sight velocity relative to the rest frame of the cosmos. Isolating this signal from the much stronger thermal Sunyaev-Zeldovich effect demands exceptionally precise multi-frequency radiometry. The thermal effect depends on the total thermal energy of the cluster gas rather than its bulk motion. When teams of astronomers applied advanced matched filter algorithms to data from orbital observatories, they uncovered an unexpected systematic offset. The clusters were not stationary relative to the cosmic microwave background frame. They were accelerating toward a distant gravitational basin at velocities exceeding 2 million miles per hour. This collective streaming motion defied explanation within the standard lambda cold dark matter paradigm. If gravity operates uniformly across an isotropic universe, mass distributions within our observable horizon cannot generate a coherent bulk flow spanning billions of light-years. Confronting this anomaly forced theorists to evaluate radical explanations regarding the pre-inflationary geometry of space. One leading hypothesis suggests that dark flow represents the gravitational influence of colossal structures residing entirely outside our observable horizon. During the earliest fractions of a second following the Big Bang, cosmic inflation stretched space exponentially, creating our visible universe as a tiny pocket embedded within a vastly larger, heterogeneous multiverse. If mass distributions beyond our cosmic event horizon possess severe density gradients, their titanic gravitational pull could impart a persistent momentum onto our entire sector of the space-time fabric. It would act like an invisible tow rope, hauling thousands of galaxy clusters in the same direction. Alternative interpretations urge caution, suggesting that systematic uncertainties in cluster gas models or residual foreground contaminations might mimic a bulk flow signal. Independent analyses utilizing different data sets have engaged in rigorous debate regarding the statistical robustness of the measurement, highlighting the delicate interplay between empirical observation and theoretical modeling in modern astrophysics. Whether dark flow represents an actual gravitational tug from beyond our horizon or an artifact of complex data processing, it underscores the persistent friction between tidy theoretical assumptions and messy observational reality. Exploring these extreme kinematic anomalies shows that our picture of the cosmos is far more intricate than our equations predict. Every attempt to map the cosmos uncovers new layers of motion and structure that push human understanding toward its limits. We remain part of a vast moving river of matter, drifting along currents whose true origins lie far beyond the limits of our observational horizon. That reality invites continuous refinement of our physical models as we probe the deepest mysteries of the universe. High-density plasma occupying the infant universe functioned as an extraordinary acoustic medium governed by a perpetual struggle between intense radiation pressure and gravitational compression. During the initial 380,000 years following the Big Bang, ordinary matter and high-energy photons were tightly coupled into a dense, opaque fluid. Photons exerted an immense outward push, striving to scatter matter across the expanding volume, while gravity worked relentlessly to pull that same matter inward toward regions of higher density. This intense competition generated colossal sound waves propagating directly through the primordial soup. Unlike acoustic waves in Earth's atmosphere, these sound waves traveled at roughly half the speed of light. They were driven by the radiation field's ferocious energy. As dark matter collapsed unhindered into invisible gravitational wells, the coupled photon-baryon fluid was driven outward, creating expanding spherical shells of dense matter centered on every major primordial concentration. A sudden historical transition permanently altered this dynamic. As the universe expanded and cooled to approximately 3000 Kelvin, free electrons and protons finally captured one another to form neutral hydrogen atoms in an epoch known as recombination. Photons instantly decoupled from ordinary matter, escaping into the void to become the cosmic microwave background radiation we observe today. Deprived of photon pressure, the outward propagating sound waves halted instantly, freezing their spherical shells of enhanced baryon density in place at a precise physical radius. This frozen acoustic footprint represents the baryon acoustic oscillation scale, a fundamental standard ruler embedded permanently within the architecture of the cosmos. The characteristic radius of these frozen shells measures roughly 150 megaparsecs, or nearly 500 million light-years across. Every galaxy cluster separated by that specific distance shares an ancestral acoustic linkage dating back to the infancy of the universe. Visualizing this scale benefits from a quantitative metaphor. Imagine striking a colossal planetary bell submerged beneath a boundless ocean of molten rock, sending a single massive seismic shockwave rippling outward. If the entire medium suddenly solidifies into stone at a precise moment, that frozen wave leaves a permanent circular ridge ringing the impact site. The distribution of matter across the cosmic web preserves that exact seismic signature written in the spatial arrangement of galaxies. Modern cosmological surveys leverage this frozen acoustic scale as an absolute yardstick for measuring the expansion history of the universe. By mapping the statistical clustering of millions of galaxies across deep space, astronomers can measure how much those acoustic shells have been stretched by the accelerated expansion of space over billions of years. This methodology provides an independent, highly robust confirmation of dark energy's influence, decoupling spatial geometry from local galactic physics. Tracing these Baryonian acoustic oscillations connects microscopic quantum phenomena with macroscopic cosmic architecture. The tiny fluctuations born during inflation were amplified into sound waves sculpted by plasma dynamics and ultimately imprinted upon the distribution of galaxies across the entire visible universe. Every galaxy wall, every colossal void, and every intersecting filament bears the silent acoustic memory of the infant cosmos. Advanced spectroscopic mapping projects continue to refine our measurement of this acoustic standard ruler across increasingly distant redshift slices. Each new dataset sharpens our understanding of how cosmic expansion accelerated over time, testing the boundaries of general relativity and probing the nature of the invisible forces shaping reality. We're reading an imprint left in the fabric of space-time, tracing the primordial fluctuations that guided the slow growth of the universe's large-scale structures. General relativity says mass warps the fabric of space-time. That warping then forces beams of starlight off straight paths as they cross the cosmos. Dramatic events like strong lensing create luminous arcs and multiple images of a single background source. A far more pervasive, subtle effect, however, dominates how we map the universe. Weak gravitational lensing operates as a statistical distortion, subtly reshaping the morphology of billions of distant galaxies through the unseen gravitational influence of intervening dark matter structures. Light originating from a primordial galaxy billions of light-years away must navigate an uneven, highly complex cosmic terrain before striking our orbital instruments. As the ancient photon stream passes through massive foreground halos, intersecting filaments, and broad sheets of dark matter, the localized gravitational potential behaves like an enormous and imperfect lens. Unlike a glass lens, a cosmic lens is invisible, made of vast concentrations of matter that give off no light but exert an overwhelming gravitational pull. Passing through these invisible gravitational wells alters the trajectory of background light in two distinct ways. Convergence scales the overall image size isotropically, while gravitational shear introduces a slight directional elongation. The background galaxies, which naturally possess a diverse array of random orientations and intrinsic shapes, are uniformly stretched along a preferred geometric axis by the foreground mass. This deformation is tiny, often shifting a galaxy's apparent profile by only a fraction of a percent. It is invisible to the naked eye when you look at any single galaxy. Isolating this subtle shear signal requires rigorous, large-scale statistical methods. An individual galaxy cannot serve as a reliable indicator of foreground mass because its natural shape might be inherently elliptical or disturbed by a recent tidal interaction. Diagnostic accuracy emerges only when astronomers aggregate the shapes of hundreds of thousands or even millions of background galaxies across a wide field of view. Computers compute average orientations and ellipticities in specific spatial bins. From that data, they extract a coherent statistical signal that maps the distribution of the invisible mass responsible for the distortion. A simple quantitative metaphor helps clarify the diagnostic process. Imagine standing behind an old, unevenly manufactured pane of glass, observing a grid of uniform tiles on a distant building. The individual tiles possess random variations in their manufacture, but the glass introduces a systematic, overarching warp across the entire field of view, stretching the visual grid along specific diagonal vectors. By analyzing the micro-distortion patterns across the entire wall of tiles, you can map the precise thickness, density fluctuations, and internal flaws of the glass pane without ever directly touching the material. Weak gravitational lensing executes this exact mathematical reconstruction on a cosmic scale. Mapping invisible mass through this technique liberated astrophysics from the severe limitations of optical observation. For centuries, researchers were constrained to auditing only what emitted electromagnetic radiation. Glowing stars, dense gas clouds, and active galactic nuclei. Weak lensing shattered that boundary, providing a direct observational tool to map the unilluminated scaffolding of the universe. It confirmed that the brilliant structures of the cosmic web are merely visible decorations sitting atop massive invisible mountains of dark matter. Modern survey telescopes deploy ultra-wide-field digital cameras capable of capturing sweeping expanses of the night sky in a single exposure, recording the faint, distorted shapes of distant galaxies in staggering quantities. High-performance computing clusters process these massive datasets, applying advanced algorithms to measure minute ellipticities, correct for atmospheric distortions, and reconstruct three-dimensional density maps of dark matter halos and sprawling filaments. These reconstructions reveal a continuous interconnected network that mirrors the theoretical predictions generated by large-scale cosmological simulations. Executing these measurements across different redshift slices allows astrophysicists to track how dark matter distributions evolved over billions of years. As ancient light travels across cosmic time, it accumulates distortions from every gravitational well it passes along the way. Tracing these cumulative shear patterns provides an independent, highly robust method for measuring the geometry of the universe and constraining the accelerating influence of dark energy. Every warped galaxy image captured by modern orbital observatories adds a vital data point to our evolving ledger of reality. The universe proves to be an intricate system where the dominant architecture remains entirely hidden from direct optical detection, yet reveals its presence through the subtle bending of passing light. We continue to decode these invisible signatures, pushing our understanding of cosmic structure ever deeper into the unlit geometry of space. Thermal radiation blanketing the entire celestial sphere preserves the oldest direct physical record of creation. The cosmic microwave background represents far more than a residual glow from the infant universe. It functions as a microscopic cartography of the primordial density fluctuations that ultimately forged every structure in existence, traversing 13.8 billion years of expanding space. These ancient photons arrive at our orbital detectors carrying an exquisite, unaltered signature of the physical conditions prevailing 380,000 years after the Big Bang. Decoupling of matter and radiation occurred when the expanding cosmos cooled sufficiently for free electrons and protons to bind into stable hydrogen atoms. Prior to this historic epoch, the universe was an opaque, high-temperature plasma where photons constantly scattered off free electrons, trapping light in a chaotic thermalized fog. Recombination rendered space transparent, allowing those trapped photons to stream freely across the void without further scattering. As the metric of space stretched over billions of years, that high-energy thermal flash red-shifted dramatically, transforming into a faint microwave background bathing every coordinate of the universe. Initial measurements of this background radiation revealed an extraordinary degree of uniformity. Across every sector of the sky, the temperature of the microwave background measured a remarkably constant 2.725 Kelvin. For early theoretical astrophysicists, this pristine uniformity presented an acute mechanical paradox. A perfectly smooth, isotropic primordial plasma would expand uniformly in all directions, permanently forbidding the gravitational collapse required to assemble stars, galaxies, and massive cosmic webs. If the infant universe possessed zero structural variations, the modern cosmos should be an utterly sterile expanse of diluted gas. Improvements in instrument sensitivity came over successive generations of orbital observatories built to measure tiny temperature differences across the sky with high precision. The launch of the Cosmic Background Explorer in 1992 gave the first clear evidence that the background radiation was not perfectly uniform. It showed microscopic temperature fluctuations of roughly 1 part in 100,000. Subsequent orbital missions, including the Wilkinson Microwave Anisotropy Probe and the Planck satellite, refined these initial measurements into high-resolution all-sky maps. Visualizing these maps reveals a colorful speckled tapestry of tiny hot and cold spots scattered across the celestial sphere. Each microscopic variation, measured in microkelvins, reflects a localized density perturbation. These perturbations were present in the primordial plasma at recombination. A simple physical metaphor helps clarify the significance of these tiny variations. Imagine standing atop a vast, perfectly calm alpine lake on a windless morning where the water surface appears entirely glass-like and uniform from a distance. Up-close spectroscopic sensors, however, reveal subtle micro-ripples and pressure gradients driven by deep thermal currents circulating beneath the surface. Those microscopic variations dictate where surface debris eventually accumulates and how aquatic currents organize themselves. The microkelvin fluctuations in the cosmic background act the same way, serving as invisible blueprints for the large-scale structures we see today. Cold spots mapped across the microwave background correspond directly to regions possessing a microscopic excess of mass density. Within those slightly denser pockets, gravitational attraction was fractionally stronger than the cosmic average, initiating a slow, cumulative pull that drew in surrounding dark matter and ordinary gas over billions of years. Conversely, warm spots represent regions of lower density, the embryonic precursors of the colossal cosmic voids that now span hundreds of millions of light-years. Transforming the speckled temperature map into a power spectrum produces an acoustic curve marked by a series of distinct peaks and troughs. Each peak corresponds to a specific harmonic frequency of the sound waves propagating through the primordial photon baryon fluid before recombination froze them in place. The first acoustic peak measures the universe's spatial curvature, showing with remarkable precision that the geometry of space is flat. Subsequent peaks encode the precise relative amounts of baryonic and dark matter, providing an independent verification across multiple scales that matches galactic surveys and weak lensing maps. Every major parameter defining our standard cosmological model is anchored directly to the statistical distribution of these primordial temperature ripples. The 2 trillion galaxies populating the modern cosmic web, the sprawling tectonic walls, and the accelerating expansion driven by dark energy are all direct macro-scale expressions of microscopic quantum fluctuations amplified by gravity across 13 billion years of evolutionary history. Spaceborne instruments continue to analyze the subtle polarization patterns embedded within the microwave background, searching for primordial gravitational waves, the elusive echo of cosmic inflation itself. Decoding these faint ripples pushes human observational capability to absolute physical limits, bridging the gap between subatomic quantum mechanics and the grand architectural geometry of the expanding universe. Physical reality reveals its grand architecture not as a collection of isolated phenomena, but as an uninterrupted multi-scale continuum governed by the relentless mathematics of gravity. Tracing the trajectory from microscopic microkelvin temperature ripples embedded within the cosmic microwave background to titanic tectonic walls spanning hundreds of millions of light-years exposes a unified physical ledger. Every structural manifestation across the expanding universe represents a direct, unbroken consequence of initial conditions established during the opening fractions of a second following the Big Bang. Subatomic quantum fluctuations operating in the infant universe served as the foundational seed perturbations for all subsequent structure formation, stretched exponentially across space during the epoch of cosmic inflation. Those microscopic density variations established the uneven gravitational landscape that dictated the destiny of matter. As the primordial plasma cooled and neutral hydrogen atoms formed, acoustic sound waves propagating through the dense photon baryon fluid were abruptly frozen in place, leaving behind an immutable standard acoustic ruler encoded within the spatial distribution of galaxies. Dark matter assumed the role of master structural architect, collapsing unhindered into invisible trenches and carving out the colossal gravitational scaffolding of the cosmic web. Ordinary baryonic matter followed those invisible contours, pouring into dense filaments, flattening into monumental planar sheets, and pooling into the brilliant galaxies that populate our modern epoch. Simultaneously, regions experiencing initial mass deficits were aggressively evacuated by surrounding gravitational siphons, forming expanding spherical voids that now dominate the volumetric architecture of reality. Comprehending this vast machinery requires viewing the cosmos as a magnificent gravitational symphony. Imagine an infinitely complex orchestral score where every individual instrument, from a dwarf galaxy drifting through a distant void to a supermassive black hole fueling a luminous quasar, executes its part under the strict baton of thermodynamic and gravitational laws. The entire composition has played out across 13.8 billion years, transforming an initial state of hyperdense, uniform thermal energy into a sprawling heterogeneous network of 2 trillion distinct galactic islands. Advanced observational instruments allow human intelligence to audit this colossal composition across space and time. Launching space telescopes, mapping weak gravitational lensing, and measuring subtle bulk flows push our observational reach to the limits of what we can measure. Humanity extracts hidden truths from stretched infrared photons and ancient microwave echoes, constructing rigorous mathematical models that reconstruct epochs preceding human history by billions of years. Realizing our position within this grand cosmic architecture induces a profound philosophical paradox. We occupy a transient, highly privileged chronological window, an era where the universe is sufficiently old to reveal its sprawling network of galaxies, yet sufficiently youthful that distant structures remain accessible across our observational threshold. Beyond this epoch, the relentless acceleration driven by dark energy will continue to push galaxies past the cosmic event horizon, plunging the future night sky into permanent, unyielding darkness. Observing a dying view endows our scientific inquiry with extraordinary urgency and purpose. We are the conscious voice of a universe that woke up, looked back at its own origins, and audited its own mass ledger. Intelligent consciousness functions not as an accidental byproduct of mindless chemistry, but as the universe's ultimate mechanism for self-reflection. Across an ocean of expanding vacuum and isolated islands, human intellect reaches across unbridgeable physical distances, decoding the ancient light of a boundless cosmos before the final silence descends. Astronomical measurements underwent a violent paradigm shift during the late 1990s. Two independent research teams set out to map the deceleration of the cosmos. Saul Perlmutter of the Lawrence Berkeley National Laboratory led one group. The other was the High Z Supernova Search Team, headed by Brian Schmidt and Adam Rees, and together they aimed to calculate how rapidly gravity was slowing the expansion of the universe. Conventional astrophysical theory dictated that the mutual gravitational attraction of all matter, both visible stars and invisible dark matter, should act as an overarching braking mechanism, gradually reducing the velocity of cosmic expansion over billions of years. Measuring this deceleration required an absolute standard candle. Astronomers used objects with uniform intrinsic luminosity, so they could reliably deduce distance from apparent brightness. Type Ia supernovae served as the celestial lighthouse. These thermonuclear explosions happen when a carbon-oxygen white dwarf in a binary system accretes enough mass from its companion, triggering a runaway detonation that reaches a standard peak brightness. By observing these distant explosions, researchers mapped recession velocity from redshift and determined true physical distance from brightness. Executing this observational strategy meant capturing light from stellar detonations billions of light-years away. Those photons peaked deep into the universe's past expansion. The foundational assumption was straightforward. By comparing recession velocities of distant supernova with local measurements, researchers expected to quantify how fast gravity was slowing the cosmic expansion. Analyzing data from dozens of distant supernovae produced a result that upended the prevailing physical models. The supernovae appeared systematically fainter than expected if the universe's expansion were indeed slowing. Accounting for this luminosity deficit required an alarming geometric adjustment. The distant supernovae were significantly farther away than predicted, which showed the universe's expansion was not decelerating under gravity. It was actively accelerating. Discovering that space is expanding at an accelerating rate introduced a profound theoretical crisis into modern physics. An invisible repulsive pressure, subsequently designated as dark energy, was actively overpowering the collective gravitational pull of trillions of galaxies. Unlike ordinary matter or dark matter, which dilute as space stretches, dark energy remains constant per unit volume of vacuum. As matter thins out across the expanding cosmic web, the unchanging negative pressure of dark energy dominates the ledger of reality, driving an exponential stretching of the space-time metric. Visualizing this repulsive mechanism requires a rigorous quantitative metaphor. Imagine inflating an industrial rubber balloon embedded with thousands of tiny metallic dots representing galaxy clusters. Normal gravitational attraction functions like microscopic elastic bands connecting the dots, attempting to pull them together against the stretching of the rubber. If you pump air into the balloon at a constant rate, the dots should gradually slow their rate of separation as the elastic tension builds up. Now, imagine replacing the air inside the balloon with a specialized gas that exerts an outward pressure proportional to the increasing surface area, causing the inflation rate to speed up exponentially. The metallic dots are flung outward at escalating velocities, and the distance between them multiplies at an accelerating pace. Dark energy operates as that expansive internal pressure, overriding the local elastic pull of gravity across the cosmos. Confronting the empirical reality of cosmic acceleration forced theorists to re-evaluate the cosmological constant originally introduced by Albert Einstein. Originally conceived as a mathematical fudge factor to maintain a static universe, Einstein discarded the term as his greatest blunder once Edwin Hubble proved the cosmos was expanding. The 1998 supernova discoveries resurrected that discarded constant, elevating it to the primary driver of cosmic evolution. Yet, understanding that a mysterious vacuum energy constitutes nearly 70% of the total mass energy inventory of the universe revealed how little contemporary physics comprehends about the fundamental nature of empty space. Space-borne observatories and advanced spectroscopic surveys were subsequently deployed to map the precise equation of state-governing dark energy, testing whether its repulsive pressure remains strictly constant across epochs or evolves over time. Every dataset returned by these instruments confirms that dark energy is alarmingly persistent, driving the expansion rate upward with unwavering mechanical authority. Uncovering this cosmic acceleration fundamentally transformed our understanding of reality. The grand architecture of filaments, walls, and voids is not locked in a permanent stable dance. It is being systematically driven apart by a hidden force embedded within the very structure of the vacuum. As this accelerated expansion continues unchecked across future epochs, the overarching geometry of the universe will ensure that every isolated island of matter is carried beyond the causal horizon, fulfilling the thermodynamic destiny of permanent, unyielding isolation. Theoretical physics faced an unprecedented intellectual crisis the moment empirical data confirmed that the expansion of the universe was accelerating. Naming the phenomenon dark energy provided a convenient label for an observed effect, but it offered zero insight into the underlying mechanism. Theorists were forced to audit the most fundamental definition of empty space, plunging into a profound conflict between general relativity and quantum mechanics, the two great pillars of modern physics that notoriously refuse to speak a common mathematical language. The most straightforward theoretical candidate for dark energy is the cosmological constant, originally introduced by Albert Einstein as a static balancing term in his field equations. Within modern quantum field theory, this constant is reinterpreted not as an arbitrary mathematical fudge factor, but as the intrinsic energy density of the vacuum itself. To understand why this concept creates a catastrophic theoretical headache, one must examine what quantum mechanics dictates about the nature of a true void. Classical intuition defines a vacuum as an absolute nothingness, a completely empty volume devoid of matter, radiation, or energy. Quantum field mechanics completely destroys this naive assumption. According to the Heisenberg uncertainty principle, energy, and time share a reciprocal relationship that permits microscopic fluctuations to manifest within any given spatial coordinate, provided they vanish within an infinitesimally brief duration. Consequently, empty space is never truly empty. It operates as a hyperdynamic churning sea of virtual particles constantly popping into existence and annihilating one another across every cubic centimeter of the cosmos. This quantum churning generates what physicists call zero-point energy, a baseline residual activity inherent to the vacuum itself. When theoretical physicists in the late 20th century attempted to calculate the total magnitude of this quantum vacuum energy by summing up all possible frequency modes across the subatomic spectrum up to geological Planck scales, they arrived at a definitive theoretical value. The resulting calculation exposed what is universally recognized as the worst prediction in the history of physical science. The theoretical energy density derived from quantum mechanics exceeded the actual observed value of dark energy by a factor of 10 to the 120th power, or 1 followed by 120 zeros. To grasp the sheer absurdity of this mathematical discrepancy, picture auditing the financial ledger of a small neighborhood corner store. If you calculate their daily revenue using standard quantum field theory, the expected earnings would dwarf the total combined economic output of every human being who has ever lived, multiplied by 1 trillion and raised to an astronomical power. Yet the cash register actually contains a single worn nickel. The theory is not merely slightly inaccurate, it is completely catastrophically detached from empirical reality. Faced with this monumental discrepancy, often termed the cosmological constant problem, theoretical physicists explored alternative explanations that decoupled dark energy from the static energy of the vacuum. One prominent hypothesis introduces a dynamic scalar field known as quintessence. Unlike a strict cosmological constant, which maintains an unyielding energy density across space and time, a quintessence field fluctuates dynamically as the universe expands. It operates more like a slow-rolling wave, evolving across cosmological epochs and potentially interacting with ordinary matter and dark matter through subtle coupling mechanisms. Proponents of the quintessence model argue that it elegantly resolves the fine-tuning puzzle. If dark energy is driven by an evolving scalar field rather than a fixed vacuum energy, its current magnitude might simply represent an intermediate stage in a long-term evolutionary trajectory, rather than a fundamental physical constant that requires absolute miraculous precision from the Big Bang. Yet, despite decades of theoretical refinement, empirical data gathered from space-borne observatories has consistently failed to detect any definitive spatial or temporal variation in dark energy. Every measurement confirms that its repulsive pressure remains stubbornly, frighteningly constant. Other theoretical frameworks abandon standard four-dimensional general relativity entirely, proposing modified gravity theories that suggest Einstein's equations break down across ultra-large cosmological scales. These models posit that what we interpret as a mysterious dark energy is actually an illusion caused by the altered behavior of gravity across intergalactic distances, where the gravitational force weakens slightly on scales spanning billions of light-years. However, rigorous testing against cosmic microwave background data and large-scale structure surveys continues to constrain these alternative geometries, leaving the standard lambda cold dark matter model standing as the most robust, if deeply puzzling, framework. The true nature of dark energy remains the ultimate unresolved frontier of modern astrophysics. We can measure its macroscopic influence with extraordinary precision, observing how it accelerates the expansion of space and drives distant galaxies across the cosmic event horizon. Yet the underlying microscopic engine powering this acceleration guards its secrets behind an impenetrable wall of mathematical contradiction. Confronting this vacuum enigma exposes the ultimate humility of human scientific inquiry. We have mapped 2 trillion galaxies, charted colossal tectonic walls, and audited the primordial acoustic ripples of the infant universe. Yet 70% of the total mass-energy inventory of reality remains governed by a force we can mathematically calculate only by invoking the most catastrophic error in intellectual history. As long as this void remains unexplained, our grand ledger of the cosmos is incomplete, awaiting a revolutionary unified theory that will finally bridge the chasm between the subatomic quantum realm and the sweeping curvature of space-time. Unrelenting cosmic acceleration dictates a severe long-term structural bifurcation across the universe. It splits the ledger of reality into 2 irreconcilable physical futures. While dark energy relentlessly drives the overarching expansion of space outward on a macro scale, overpowering the collective pull of distant matter, its repulsive pressure encounters a localized barrier when confronting systems bound together by intense gravitational fields. Understanding this mechanical division requires examining the fierce competition between vacuum acceleration and bound mass concentrations across future epochs. Dark energy does not possess the capacity to tear apart every structure in existence. Its expansive influence is strictly governed by spatial scale and local mass density. Within regions where matter is densely packed and gravitational potentials are extraordinarily deep, gravity easily wins the localized battle against cosmic expansion. The repulsive pressure of the vacuum is a constant weak force operating over vast intergalactic distances. It cannot overcome the robust gravitational bonds holding individual stellar systems or compact galaxy clusters together. This localized victory of gravity ensures that our immediate cosmic neighborhood will experience a distinct evolutionary path compared to the rest of the expanding universe. The Milky Way and the neighboring Andromeda Galaxy are currently hurtling toward each other on a direct gravitational collision course at hundreds of thousands of miles per hour. Driven by mutual attraction, these 2 massive spiral systems are destined to merge over the next 4 billion years. They will combine their hundreds of billions of stars, gas reserves, and dark matter halos into a single massive elliptical or rejuvenated stellar formation, often designated by astronomers as Milkomeda. Other members of our local group, including the Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of smaller dwarf satellite galaxies, will likewise be dragged into this unified gravitational well. Bound securely by shared orbital momentum and deep dark matter roots, the local group will remain physically intact. The stars will continue to burn, and planetary systems will maintain their orbits. Internal stellar dynamics will proceed largely unbothered by the accelerating expansion occurring in the vast spaces beyond our immediate frontier. Yet this local preservation stands in stark, tragic contrast to the fate awaiting everything outside our gravitational anchorage. Every external structure residing beyond the boundaries of the local group is completely vulnerable to the relentless stretching of space. As dark energy continues to drive exponential expansion, the intergalactic distances separating our merged home from neighboring superclusters, monumental walls, and distant voids will grow at accelerating rates. Those external structures are not merely drifting away, they are crossing the cosmic event horizon. As each distant galaxy passes beyond that invisible causal boundary, The volume of space expanding between us and them reaches a metric velocity exceeding the speed of light. Their final photons of light struggle against the stretching space and fall into permanent obscurity. The grand tapestry of 2 trillion galaxies is systematically erased from our future observational ledger, one structural node at a time. Imagine a cluster of maritime islands linked by shallow land bridges in the middle of an ocean whose level is rising exponentially. Nearby coasts fuse, distant chains are swept beyond the horizon. Islands sitting close together can fuse their coastlines and merge into a single massive continent through mutual tectonic drift. Every distant island chain out in the open sea is swept away beyond the horizon as the intervening water stretches outward, disappearing from sight. The fused central continent stays intact, but it is permanently marooned on a boundless sea. The same isolation awaits our local stellar remnant. Over billions of years, the night sky will grow steadily poorer and lose what we now see. The majestic spiral arms of distant systems will fade from view. Neighboring clusters will slip over the horizon into eternal silence. Eventually, even the closest external galaxy will cross the threshold. Our merged stellar core will be completely cut off from the rest of the universe. Future generations living on planets around suns in our isolated remnant will inherit a sharply restricted view of the cosmos. When future astronomers train their telescopes on the void, they will map a sky with no external galaxies. They will observe our merged stellar system and study the remnants of local gas clouds. They will calculate the dynamics of their immediate neighborhood, unaware of the vast, vibrant cosmos that once surrounded them. The sprawling network of filaments, walls, and voids will have vanished, hidden beyond an impassable cosmic horizon as the space beyond grows unreachable. Confronting this ultimate isolation forces a profound philosophical realization regarding the transient nature of human privilege. We occupy a narrow, exceptionally rare chronological window in cosmic history. We live during an epoch where the universe is old enough to have constructed a sprawling web of 2 trillion galaxies, yet young enough that their ancient light can still reach our instruments before the cosmic event horizon closes permanently. We are the witnesses to a fleeting panoramic view, auditing an infinite library of worlds, just as the lights in the grand hall are beginning to go out one by one.